a postdoc at the ITM laboratory at NASA Goddard Space Flight Center. And today I would like to present you an overview of the Southern Argentina Agile Meteor Radar Orbital System, a dedicated meteor radar survey monitoring the sub-millimeter Southern Hemisphere meteor environment. In this talk, we will introduce some aspects about the hardware, observing, and analysis methodology. Then we will move on and elaborate on some of the unique capabilities of the system to survey the meteor environment at austral latitudes. This work includes the combined effort of colleagues at Goddard Space Flight Center, the Institute of Astronomy in Hawaii, the Estación Astronómica in Rio Grande, and the Astronomy University at La Plata, Argentina. SAMR is located in the city of Rio Grande, Argentina, and is therefore well suited to observe the southern hemisphere sky. SAMR is an all-sky 64 kilowatt backscatter radar currently with 4 remote receiving stations used to determine meteoroid orbits. The main station hosts the 5 antenna interferometric array consisting of 3-element cross-Yagis receivers and 3-element cross-Yagi transmitting antenna transmitted at 32.55 MHz. SAMR is an agile radar system. It enables the selection of several transmitting antenna configurations. Prior to 2019, SAMR transmitted with an array of 8 cross-Yagi antennas with variable phasing. By selecting individual phase in the antennas, the combined gain pattern could be modified to suit a particular experiment. For instance, a very narrow beam pattern for meteor head echoes observations, or a broad, seemingly all-sky pattern for meteor shower surveys. A part of the upgrade in 2019, SAMR currently operates a single 3-cross Yagi antenna with a smooth all-sky beam pattern as part of the Meteor Survey program. Other upgrades include low-noise amplifiers and improved signal filtering electronics, enabling the detection of fainter meteors. In addition, other upgrades include software routines for overdense meteor detections. After the upgrades, the average meteor rate showed a 2 to 3 times increase compared to previous years. SAMR-OS is funded through a NASA Engineering and Safety Center assessment, and the goal is to provide reliable near real-time monitoring of meteor activity in the southern hemisphere. Specific engineering products include daily reports to NASA NESC with orbits and fluxes for known meteor showers and other shower candidates. Meteor speeds are estimated through the time-of-flight method and corrected with an empirical deceleration function. Shower fluxes are estimated from the debiased meteor rates and the collected area for the system. Science projects are also a priority. For instance, characterizing and surveying high-latitude southern showers, mapping sporadic background sources, and southern shower outbursts. Some of the fundamentals of meteor detections with a backscatter radar can be illustrated in the following slides. Simplifying things a bit, meteors are detected as a signal echo scattered from meteor trains. The main site, the radar receivers, listens to the echo of ionized meteor trains meeting at the specular point, which dictates that meteor radiants are at right angles with respect to the echo direction. The received signal amplitude displays the usual Fresnel diffraction pattern analog to the illumination of a razor-thin edge. In this figure, we present the idealized amplitude signal of a meteor for several electron line density values, starting as an underdense event up to the overdense regime. The interferometer provides radiant directions with an average uncertainties of about half a degree. By adding multiple receiving stations off the main site, the additional scattering points along the meteor train allow an estimate of the true meteor trajectory. At the remote stations, the receivers detect slightly forward scattered signals from the main site. The time delays with respect to the main site are used to establish the meteor speed using the time-of-flight method. And when combined with the meteor direction, the meteor orbit is computed. The picture on the left shows the container housing the receiver at one of the remote stations. The receiver antennas and the remote sites are identical to the receiver and transmitter antennas at the main site. Again, this is a simplification of the principles behind the detection of meteors. Effects such as initial radius effect, Faraday rotation, and meteor diffusion are considered when correcting the observed meteor rates. This figure here shows the stacked amplitude for an underdense meteor traveling at about 48 km per second observed at the main site, plus 4 remote stations. The meteor detection software identifies the Frenet profiles, blue line, adding a smoothed filter version, shown as the light red line. The inflection points, marked by a yellow line, are used to establish the time peaks for the event as seen at each site. The red line estimates a single peak. So the principles illustrated in previous slides are sufficient to determine meteor orbits. On average, 1,000 to 3,000 meteor orbits were detected daily with the original configuration of SAMR. In the years, this is for the years 2012 through 2019. This figure shows the radiant locations in sun-center ecliptic coordinates of the 34 new showers identified in the first SAMR-OS wavelet-based shower survey in the period of 2012 to 2015. In this study, 4 years' worth of observations were used, totaling roughly 1 million orbits. Most of the new showers are located along the South Toroidal ring. This study lacked a deceleration correction, preventing more accurate orbital element estimates. This empirical meteor deceleration correction has been included in the upgrades in 2019. SAMR-OS is sensitive to faint meteors down to the 9th magnitude, or equivalently down to 10 to the minus 8 kilograms or 0.3 millimeter meteorites. This translates into sub-millimeter size and fairly evolved meteorites. Therefore, this enables SAMR-OS to probe meteoroids belonging to the sporadic sources and showers. Here we show an all-sky radiant density map with almost 8 years of observations with SAMR-OS in the period of 2012 through early 2019. This sun-center view in ecliptic coordinates clearly shows the helion, antihelion, south toroidal, and apex sporadic regions. For reference, the apex is at the center of the plot at 270 and marks the direction of Earth's motion. The sporadic background is more prominent as a result of the sensitivity of the system. Embedded in the sporadic background, one can identify some strong showers such as the daytime sextantids, the daytime aretids, the eta quarids, the south delta quarids, and the southern and northern taurids. Located at nearly 54 degrees south in latitude, the coverage north of the ecliptic is limited, as the figure suggests. Here we compare side by side radar and optical all-sky meteor surveys in the same sun-center ecliptic coordinates. On the left, we have a previous SAMR-OS all-sky radar plot, and on the right, 6 years of optical meteor surveillance with the CAMS network. It is clear how these two systems probe two different size regimes of the meteor population at about 1 AU. Optical surveys probe larger, centimeter-sized, younger meteoroids in streams, producing showers that clearly stand out above the rather diffuse sporadic background. Also evident is the size-dependent evolution affecting the main size regimes probed by radar and optical surveys. This figure also highlights the ability of the meteor radars to probe meteor activity during daytime hours, something not possible in optical surveys. As mentioned earlier, the recent hardware and software updates in 2019 improved SAMR-OS sensitivity, sky coverage, and readiness to report meteor observations. Meteor radiant plots, like the one shown on the left, display meteor detections, height, and speed distribution every 20 minutes. Over the course of a day, more than 10,000 meteor orbits are recorded on average. The figure on the right illustrates the detection gathered every week. This figure captures the structures in the sporadic sources in great detail. A 3D wavelet-based algorithm developed in-house is included as part of the software upgrades of SAMR-OS, and is used to identify and characterize meteor showers. The 3D wavelet technique excels in identifying clusters in radiant distributions in the space of geocentric sun-center ecliptic coordinates and speed. This is particularly useful as meteor showers cluster in such coordinate and time. The wavelet transform maps shower score in radiant space into local wavelet coefficient maxima. On the right, we have an animated plot of the sun-center radiant distribution as a function of time, color-coded by speed, and on the left, the wavelet transform at a speed of 37.7 kilometers per second. The wavelet transform is used to enhance clustering at any speed of interest. If you look on the right, some showers like the daytime sextantids, daytime aretids, the northern and southern aquilids, the south delta aquarids, and the lambda arietids are clearly visible as local wavelength coefficient maxima. The south delta Aquarids is the strongest shower visible in the south, peaking at about a solar longitude of 125 degrees. This technique is used to detect and track meteor showers over time, separating them from the sporadic background. So as you can see on the right, the Wheeler transform smoothes out all the distribution of radiance shown on the left and highlights the presence of showers as clusters in this space of variables. This animation here illustrates how the wavelet transform can be used to identify shower cores and shower candidates in daily observations with the system. The animation is a compilation of the daily reports sent to NASA and ESC assessing meteor activity. The wavelet transform is used to draw circles at the location of shower cores on top of the radiant density map. The density map is estimated with the number of meteors within 2 degrees of each other. The map shows the showers identified and their strength in units of the combined spread or total error in the data. That variable is called x sigma. A shower with an x sigma value of 5 means the shower is 5 times the total error above the annual mean. Showers with x sigma values above 2.5 are labeled in this plot. Showers candidates are labeled as ID followed by the number of candidates each day. The animation includes data here from January 1st through December 31st, 2020. Reports also include flux measurements for each shower identified in daily operations with the system. Here we show an example of a report with shower radiance, orbital elements, and fluxes from the daily bias, meteor rates, and the radar collecting area. The figures on the left, second and third row show shower meteoroids fluxes for the south and northern delta Aquarids, Pisces Austrinids, and the alpha Capricornids. For each shower, a 6 magnitude equivalent flux is used to estimate the zenithal audit rates. Previous daily flux measurements are also stored for each shower and included as part of the analysis. Below is an example of flux measurements for the south delta Aquarids over a period of approximately 30 days in 2020. And on the right, you could see an example of the daily reports sent to NASA and ESC. Besides the daily assessment of meteor activity, research programs with SAMR-OS remain a priority. Here, we briefly include some recent results published with the radar. For instance, this figure is from a decadal survey study of the sporadic meteor mass indices in the southern hemisphere for the period of 2008 through 2018. The solid line is the running mean with a 10-degree window of solar longitude. The mean mass index value determined for the sporadic sources based from the black curve is 1.98 plus minus 0.03. Another recent study results in the discovery of another outburst in the Beta Tucanic meteor shower. Some shower outbursts can be relatively mild enough to only raise the flux slightly above the radar detection threshold, making observations of it possible for the first time. This shower has not been visible in previous years with SAMR-OS. The plot at the bottom shows the absence of the shower in previous years as measured with the wavelet transform. The peak in blue shows a strong detection of the event. Asteroid 2006 CS, a NEO, was found as a promising candidate for the parent of the shower based on the D criterion. More recently, a second outburst was detected south of the South Auroral Ring. The outburst of the Alpha Carinae meteor shower peaked at about 21 to 22 hours UT time on October 14, 2020, at a solar longitude of 201 degrees 0.7, lasting 7 days, and it was successfully flagged in our daily reports. On the upper right, a modified version of the report on October 14 shows the peak of the outburst flagged as a shower candidate ID0. This was a strong detection, 16 times the certainty above the annual mean. This shower was not detected in previous year with the radar as shown in the bottom plot. We reported hourly shower fluxes insert in the figure at the bottom, and mean daily fluxes, as shown in the figure in the upper left. We estimate a zenithal hourly rate of about 6, assuming a mass index value of 2, which is comparable to other known showers, and also estimated a maximum zenithal hourly rate of about 44 if we assume a mass index of 1.65. All previous outbursts detected south-equatorial rain, for instance the Volantis, the Beta Tucanid, and the Alpha Carinids, share orbits that resemble those of a short-period object with similar orientation. Last but not least, another recent study focused on a new method to obtain absolute velocity and orbital information of meteor head echoes measured with the system. Highlighting the agile capability of the radar, this study included 71 Beta Tucanid meteors and were detected with the A antenna transmitter configuration. All transmitting antennas operated in phase, resulting in a narrow beam with a 3 dB decrease of power at approximately 8 degrees off zenith at an altitude of 100 kilometers. The top panel showed the range time intensity plots from the receiver stations, and they decoded a normal range derived from the respective head echoes and detected. As validation of the method in the study, we also included optical detections with a small network of narrow field cameras. The derived trajectories for these Beta Taurid meteors from optical and radar measurements are shown in the plot below. This is my last slide, and I hope that this presentation provided a good summary of the capabilities and potential of summer observations for high-quality research on meteor science. Thank you very much.